Good evening. Welcome back to the module Communication Theory, Learning Outcome 2. In previous session, we studied about the ergodic random process, stationary random process, then Whitson stationary random process. The condition for Whitson stationary random process is that the mean of the random process is constant and the autocorrelation function of the random process is depend only on the time difference T1 and T2, and it does not depend on the observation time of the random process T1 and T2. If these two conditions are satisfied, then that kind of random process is called a Whitson stationary random process. Example for Whitson stationary random process, randomly phased sinusoid. After that, we studied about the Gaussian random process. The random process is called the Gaussian random process, whose joint and conditional PDF functions depends only on the Gaussian functions. Then that kind of random process is called the Gaussian random process, and it has the several properties. The first property of the Gaussian random process is that the Gaussian random process is completely described by its mean and autocorrelation function. That is the first property of the Gaussian random process. And the linear operation of the Gaussian random process produces the another random process, another Gaussian random process. That is the second property of the Gaussian random process. And the third property is that if the Gaussian random process satisfy the condition Whitson stationary, then that random process also we can call it the strictly stationary random process. Okay, these are the important properties of the Gaussian random process. After that, we studied about the power spectrum calculation from the given random process. So the power spectrum of the random process would be calculated by taking Fourier transform of the autocorrelation function. Okay, in the previous session, we derived an expression to find out the power spectrum of the random process, that is randomly phased sinusoid. Finally, we got the expression for the power spectrum of the randomly phased sinusoid, which depends only on the frequency difference and the frequency summation. Okay. So with that continuation, in today's session, we are going to discuss a few more points in power spectrum analysis. After that, we are going to discuss about the filtering of the random process. So this is so just you can recap these some important formulas from the previous session. So this is the basic formula for to find out the power spectrum of the given random process V of t. So that is G B of f equal to Fourier transform of R V of tau, which is equal to integration minus infinity to plus infinity R V of tau e power minus j 2 pi f t d tau, right? Where the R V of tau is the autocorrelation function of the random process V of t. Okay, the capital F indicate the function Fourier transform. So that the power spectrum of the randomly phased sinusoid is calculated by using that autocorrelation function of the randomly phased sinusoid. Okay, so the autocorrelation function of the randomly phased sinusoid is R V of tau equal to a squared by 2 cos 2 pi f naught tau, where a is the magnitude or amplitude of the randomly phased sinusoid function. And by taking the Fourier transform of this autocorrelation function, we are getting the power spectrum, that is G B of f equal to a squared by 4 del function. The del indicate the del function, delta function. So which means that it has the impulse only at the function equal to 0. That is the difference f minus f naught equal to 0. Then it has the magnetic impulse R1. So del f minus f naught plus a square by 2, a square by 4, del f plus f naught. So f minus f naught is the difference frequency component, f plus f naught is some frequency component. So this is the final expression for the power spectrum of randomly phased sinusoid function. And then second example is random digital waves. Why we are telling the digital wave is random means the random is present in the digital wave in its delay and in its amplitude. So that we are telling it's a random digital waves. And for this also we can find out the power spectrum. So for this random digital wave, the autocorrelation function is sigma squared capital gamma of tau by d. So where the capital gamma is the triangular function, right? So by taking the Fourier transform of this autocorrelation function of random digital wave, we are getting the power spectrum, which is final expression for the power spectrum of the random digital wave is sigma squared d sinc squared f into d. Okay. So finally, it is coming with the sinc function. So for randomly digital, because it is like a rectangular pulse, that's why the in frequency domain it has the sinc function. But if you see that because of sinusoidal, it has only one frequency component. It is represented by the only del function. So you can see here the waveform representation of the power spectrum of both randomly phased sinusoid and random digital waves. The first figure A shows the waveform of the frequency domain representation of the power spectrum of the randomly phased sinusoid. And you can observe here only at a frequency f naught there is a impulse with a magnitude of a squared by 4 or amplitude of a squared by 4. Okay, so in negative minus f naught the same magnitude. So so actually the frequency component present in that randomly phased sinusoid is only one frequency component f naught. For our mathematical convenience, we are showing both negative and positive side, real axis and imaginary axis, right? And in the second waveform shows the power spectrum waveform of the digital random wave. So it is a sinc function, and you can see from this diagram only at the frequency f equal to 0, which means that it's a DC component. F0 means it is a DC component. So at that f equal to 0, it has the maximum magnitude or amplitude, that is sigma square d. Okay, then the period is varies from minus 1 by d to plus 1 by d for one sinc pulse. So the another another the difference between these two power spectrum is the randomly phased sinusoid, it has only one frequency component, whereas the random digital wave it has the n number of frequency components. It varies from minus infinity to plus infinity, because a sinc pulse it has the large number of frequency components, infinite number of frequency components. So that is the main difference between these two waveforms. So we'll see the proof how we are getting that final expression for the power spectrum of random digital wave. So this is the autocorrelation function. It's a triangular. It is function of triangular function, and the final expression is sigma square power spectrum. Final expression is sigma square d sinc squared f into d. F is the frequency of the wave, random digital wave. Okay, and d is the duration of the pulse. Capital D is the duration of the pulse, right? So so in order to get the expression for the power spectrum, let us take the autocorrelation function, that is rv up tau, because we know that it is a function of triangular function. So this graph shows the autocorrelation function of the random digital wave. So it is very the duration of the autocorrelation function varies from minus d to plus d, and the maximum magnitude at origin 0, which is sigma squared, right? So in this graph we can split into four regions, like minus infinity to minus d one region, then minus d to 0 another region, there is one slope. So minus d to 0 is one slope, and 0 to d is another slope, and d to infinity is another region. So totally four region is there. So by integrating these four region we can able to get the what is the power of the random digital waves. But you can see from this rectangular, triangular waveform. So the region minus infinity to minus d and d to infinity 0. The magnitude is 0. So you can no need to find out the integration. So only these two slope we have to consider. That is minus d to 0, one slope, and 0 to d another slope. So for our convenience, we can modify this autocorrelation function as a signal, okay, as a random signal x of t. Okay, so because of this is we are considering d to 0, considering one slope. This slope is written as t plus d into sigma square d for the interval of minus d to 0. That means this the negative slope minus d to 0. So, for example, if you put the time t equal to minus d, so it becomes 0. So the amplitude actually is 0. Then if you put the time t equal to 0, okay, then d cancels sigma squared. So at the time t equal to 0, it has the magnitude sigma squared. So in that way, we have to rewrite this autocorrelation function as a waveform equation x of t. Similarly, for the another slope 0 to t, we are writing minus t to d sigma squared by t for the interval of 0 to d. Now we can apply the normal Fourier transform for this x of t. So we are getting x of omega. So x of omega equal to because of it has the two region minus d to 0 and 0 to d. We have to take the two integration parts. Okay. Since sigma squared d is constant, you can take outside. And for the first region, the integration varies from minus d to 0. So minus d to 0, the into t plus d into e power minus j omega t dt. That is the Fourier transform of the first slope. And similarly for the Fourier transform of the second slope, the region varies from 0 to d. You can note down this integration. It has the two function, that is t and e power minus j omega t. So we need to apply the integration by parts formula. So this is the formula for the integration by parts. That is integration uv dx equal to u integration v dx minus integration of du dx integration v dx into dx. So by using this formula, we can expand the previous equation by using that integration by parts. So sigma squared d is constant, take outside, and uh, t plus d we have to keep as it is. Then the second term we have to integrate. So if you integrate the e power minus j omega t, again it will be e power minus j omega t. Because of it is function of function, if you integrate minus j omega t, it will give the minus j omega. It should be written in the denominator. And minus integration into, we have to differentiate the first term u, that is t plus d. If you differentiate, it becomes 1. And then we have to integrate the e power minus j omega t. So e power minus j omega t, if you integrate, again it becomes e power minus j omega t. Because of function of function, minus j omega t equal to minus j omega. It should be written in the denominator and into dt. Then apply the limit minus d to 0. Similarly, we can expand, we can apply the uv formula for the second term, right? So we are getting these things, right? Because here there is a negative, here minus 1 is coming. But here t, so that here plus 1 is coming. That is the difference. So minus plus here, here minus. So here what we are doing, uh, so we need to integrate this term under this term. So we can keep first term as it is, and coming to the second term, if we again we have to integrate this e power minus j omega t. So e power minus j omega t, then minus j omega is coming, but already minus j omega in the denominator, so minus j omega whole squared. So here the minus j whole squared equal to minus j whole squared equal to minus 1, because minus plus j squared equal to minus 1. So finally, so minus j whole squared equal to minus 1. but already there is a negative sign is there, so it becomes positive. So finally, after integrating, it becomes e power minus j omega t by omega squared. But coming to the second term, you can see the minus minus it become plus. But minus j whole square equal to minus one. That's why here minus is coming. Clear? So minus e power minus j omega t by omega square. Then the limit d to 0. Then now we have to apply the upper and the lower limit, right? After applying upper and the lower limit, we are getting that the first from the first term there is a three for our first part there is a three terms, and from the second part there is a three terms is coming after applying upper and the lower limit. But you can see here the minus d by j omega, here plus d by j omega, it will be cancelled, right? But 1 plus omega square, 1 plus omega square becomes 2 by omega square. Similarly, you can see here the minus e power j omega d by omega square. Here also minus e power minus j omega d by omega square. So here 1 by omega square is common, take outside. So minus 1 by omega square, and then the remaining term is the exponential term. We can write e power j omega t plus e power minus j omega t. For convenience, we can multiply both numerator denominator by 2 in order to make this exponential term by to apply the Euler identity. So e power j theta in plus e power minus j theta divided by 2 equal to cos theta. So for that purpose, we are multiplying both numerator denominator by 2. So now you can see here 2 by omega squared is common, take outside. So already sigma squared by d is there, then 2 by omega squared. So it becomes 1 minus cos omega d. Now we can apply the one more formula to simplify this expression. So 1 minus cos theta formula. So the 1 minus cos theta equal to 2 sine squared x by 1 minus cos x equal to 2 sine squared x by 2. So that we are writing that power spectrum of the random digital wave x of omega equal to sigma squared d. Here also we are multiplying both numerator denominator by d in order to for our convenient. So we are multiplying both numerator and the denominator by capital D. That's why here sigma square d, because in previous equation there is no, in a numerator there is no d, but here it is coming. So sigma square d. Then because of multiplying d, it becomes omega d squared. So 2 1 minus cos omega d, again one more 2 is coming. So 2 to 4, it should be coming into the denominator. So it becomes omega d by whole squared. And sine squared x by 2. So here x is omega d, so omega d by 2. And we can rewrite this expression whole squared. You can take the both numerator denominator square outside, so that you can write like sine omega d by 2 divided by omega d by 2 whole squared. So it is this formula for sine x, omega x by omega x, or sine pi x by pi x. If you substitute omega equal to 2 pi f, so 2 will be cancelled. So pi f d is coming. Similarly, in denominator also pi ft is coming. So sine pi x divided by pi s equal to sinc x. So that we can simplify this expression like sigma square d into sinc squared fd. Okay, this is the final expression for the power spectrum of the random digital wave. Then we consider the one more example for the to calculate the power spectrum from the random signal. Now here we consider the finite duration, or we can call it truncated random signal, that is Vt of t. We are truncating up to one period, so that it is varies from minus t by 2 to plus t by 2, where t is the period of the random signal, right? So which is equal to V of t. So V of t is available only for the modulus of t less than t by 2, otherwise it becomes 0. So from this finite duration random signal, we can find out what is the magnitude, or what is the power of the truncated random signal, right? So we can apply the Fourier transform. So by applying Fourier transform, actually we can get the frequency component of the truncated random signal, right? So Vt of f equal to, so this is the general formula for the Fourier transform. So it is varies from minus infinity to plus infinity vt of t e power minus j omega t dt. But it is this signal is truncated only to the duration of minus t by 2 to plus t by 2. So that the minus infinity to plus infinity replaced by minus t by 2 to plus t by 2. Then substitute that corresponding signal is v of t. So originally it is vt of t. So for vt of t range is minus infinity to plus infinity, but the magnitude is available only within this period of minus t by 2 to plus t by 2. So that is the difference here. You can see here we are using that subscript t, capital T. Here there is no subscript t. Only for this the duration minus t by 2 to plus t by 2. Okay. And so our aim is we want to find out what is the power spectrum of the truncated random signal. So now we can take the Rayleigh energy theorem formula. So this is that energy formula to find out the random signal v of t. So that is minus here we are not applying the Fourier transform, right? So only we are squaring the random signal and then integrating over the interval minus t by 2 to plus t by 2. That's all. Then it will be in frequency domain. We can find out this is equal to in frequency domain, which is minus infinity to plus infinity bt squared of f into df. Right. Then the corresponding average power from the Rayleigh energy theorem we can find out. So the power p equal to the limit t tends to infinity minus integration minus t by 2 to plus t by 2 expectation of p squared of t dt, which means that we have to integrate the average value of the random process. The expectation indicate the average value of the given random process, right? Right. And so further we can interchange. We are interchanging the expectation and the integration for our simplification purpose. Then finally we can see that the average power of the random signal is in frequency domain. We are representing in frequency domain, that is minus infinity to plus infinity limit t tends to infinity 1 by t expectation of modulus of v of f squared df. This is general formula to find out the average power of the random signal in frequency domain, right? Okay, but we here please note down here we are not finding the power by using that Fourier transform. We are not using any autocorrelation function. By using Rayleigh energy theorem, we are finding the average power. This is another way of finding the average power of the random signal using the Rayleigh energy theorem. So finally, we are getting that the power spectrum of the random process v of t or random signal v of t, which is g capital G v of f equal to limit t tends to infinity 1 by t expectation of modulus of v of f squared, right? By using the Rayleigh energy theorem. But we can also find out the power spectrum by using that Fourier transform of autocorrelation function. That is G B of f equal to Fourier transform of R, the autocorrelation function R V of tau, capital R V of tau. Right? We know that tau is the delay or the time difference between T1 and T2. So proof. So we know that the expectation of modulus of V of f squared. Okay. In frequency domain, we are finding that average power of the random process, that is expectation of P of f, V conjugate of f. Here we are not representing in time domain. This is in frequency domain, so that there is no different frequency component. Frequency component is same, but we are taking conjugate. We are taking V of f, V conjugate of f, right? Then in frequency domain, this is actually we can represent in terms of Fourier transform, right? So this is the Fourier transform of the autocorrelation of the random process. That is the double integration minus t2 to plus t by 2, right? And the expectation of v of t, v of lambda. Here the t lambda is that different time where we took the random process. But usually we are using the T1, T2, but in this we are using that t is one time and lambda is another time, right? So the expectation of v of t, v of lambda, e power minus j omega t minus lambda dt d lambda. So we are doing the double integration of the autocorrelation function to find out the power spectrum of the given random process v of t. And we can replace this expectation of v of t into v of lambda by autocorrelation. So which is equal to autocorrelation rv of t comma lambda. It's a time difference t minus lambda. So here we are using two variable t, small t and lambda. So this t minus lambda is replaced by tau, and t is replaced by mu. So this t and lambda is mapped to mu and tau. Is another new random variable. Okay, for integration, for double integration. Okay, for the region of tau mu plane. I will show that how the random variable t and lambda they are changing with mu and tau. So here you can see here this graph shows the integration of the tau mu plane for double integration. So here the x-axis is that variable tau and the y-axis variable mu. The range of the x-axis varies from minus t to plus t, and it has the two region like minus t to 0 one in one region we can integrate, then 0 to t is another region we can integrate. There are two integration in the x-axis, and in y-axis also you can see in mu it varies from minus t by 2 to plus t by 2, and then here it also it can be split into two region. The first region in the y-axis mu is minus t by 2 to small tau plus t by 2. That is the one region, and the second region in y-axis which varies from tau minus t by 2 to plus t by 2, right? So these are the limits of the integration we are taking from this tau mu plane, because in this we are having the double integration. That's why we have to consider all the limits. So you can see here now the expectation of this v of f squared equal to minus t to 0 autocorrelation function r v of tau e power minus j omega tau d tau, because we are changing the variable t to mu and lambda to tau, so that here it becomes tau, and another integration varies from minus t by 2 to tau plus t by 2 d mu. So similarly for the second term, we are using that remaining region 0 to t for the tau, and for mu it is varies from tau minus t by 2 to tau by 2, so t by 2. If you integrate d mu, it becomes mu. Then apply the upper and the lower limit, it becomes t plus tau. Similarly, if you integrate this term, finally we are getting t minus tau. So that after applying the first integration, the expectation of v of f squared equal to minus t to 0 r v of tau e power minus j omega tau t plus tau. How the t plus tau is coming means by integrating the first term, this one. So because the d mu equal to mu, then apply the upper limit and the lower limit. So t by 2, this minus t by 2 becomes a plus t by 2 because it is a lower limit. So minus minus plus. So t by 2, it becomes t. So t plus tau. But here the upper limit is t by 2, lower limit is minus tau plus t by 2. So that it becomes a t minus tau. So here we are getting t minus tau, right? Then then we have to do the second integration. Okay, so after doing that second integration, so before that we can combine these two terms. This you want to simplify this term, that is capital T plus tau and t minus tau. So this t by taking this condition tau equal to minus tau, we can rewrite these two terms into a single term. So that we are writing integration minus t2 plus t 1 minus modulus tau by t. So if you cross multiply, it becomes t minus modulus tau. If tau is tau equal to positive means 1 minus t minus tau, tau is negative means t plus tau is coming. but in denominator t is we added so that you have to multiply here t, okay, into r v of tau e power minus j omega tau into d tau. So so finally we simplified that the power average power of the random process it is coming like a Fourier transform of the autocorrelation function, but this term is extra. So by we have to apply the condition that when limit t tends to infinity, so what happens, anything by infinity it becomes zero, so that the second term will be vanishes at t tends to infinity. So therefore the limit t tends to infinity 1 by t, this is coming into the left side, so 1 by t expectation of v of f squared equal to minus infinity plus infinity the autocorrelation function rv of tau e power minus j omega tau d tau. So this is the Fourier transform of the autocorrelation function of the random process v of t. So therefore, the power spectrum is gv of f equal to the Fourier transform of rv of tau. So here we are calculating the power spectrum of the random process by applying Fourier transform into the autocorrelation function. Now consider the superposition concept in the random process. So for that you can consider the two random process u of t and w of t, and assume that both are jointly stationary random process. And because of we are considering two different random process, we can find out what is the cross correlation of the random process u of t and w of t. So which is equal to r u w of t1 and t2, because we are taking the random process at u of t at the time t1 and w of t at the time t2. So it becomes an r u w of t1 minus t2. Finally the autocorrelation function is represented by time difference t1 minus t2. Now let us take the another random variable random process z of t. So z of t is sum of the two random process, different random process, that is v of t plus or minus w of t. Now we can find out what is the autocorrelation for the z of t. So the z of t1 minus t2, you can note down here both random process are the same time. So v of t and w of t, not t1 and t2. So what we will do in order to find out the autocorrelation function for the z of t, we can take the expectation of the v of t and w of t at the time t1 and v of t and w of t at the time t2. So if you multiply these two terms, it can generate the four terms, and from this you can see the first term and the last term is the generate the autocorrelation function, but the second term and the third term generate the cross correlation function. So finally, the autocorrelation of the random process is z of t. It has the rv of tau plus rw of tau plus or minus r u w of tau plus r w v of tau. Here these two terms is cross correlation function. First two is autocorrelation function. So by using this R z of tau, we can find out what is the power spectrum of this random process z of t. So which is g z of f equal to gv of f plus gw of f plus or minus g vw of f plus g wv of f. So here the GWV of f is the cross power spectral density. Okay, it's the cross power spectral density, and we can this cross power spectral density will be vanishes if the random process u of t and v of t are uncorrelated to each other. So which means that the product of mean of random process u and v and w equal to 0. So therefore, you can say that the cross correlation function will be 0. That is r u w of tau r v w v of tau equal to 0. So under this condition, we can rewrite the autocorrelation function of the random process z of t. It depends only on the r v of tau and r w of tau. Then the corresponding power spectrum g z of f equal to g v of f plus g w of f, because the cross power spectral density will be vanishes since u of t and w of t are uncorrelated to each other. Okay. So that is the concept of superposition. In superposition, we are adding two different random processes, and we are observing what is the power spectrum, what is the autocorrelation function, and average power also. You can find out the average power. When we'll get the average power of the random process means at tau equal to 0. If you put tau equal to 0 in the autocorrelation function, it will give the mean square value, or we can call the average power, that is z squared bar equal to v squared bar plus w squared bar. So that finally we are observing that the random process satisfying the superposition for autocorrelation and superposition for power spectrum and superposition for the average power. Okay, superposition means if we add the two different random process, that is equal to the sum of the two random process, right? That is the meaning of superposition. Then the modulation, we can consider the random process for the modulation. So the modulation operation z of t equal to v of t cos omega t plus pi. So the general mathematical equation for the modulated signal, where v of t is the magnitude. Okay, so it's a stationary random signal v of t, and pi is the random phase which is independent of v of t. Okay, and it is uniformly distributed over the 2 pi radians. Okay, like that we are taking considering one modulated signal z of t, and we are finding that autocorrelation for this signal. So if you find out the autocorrelation, then it is we have to take the cosine function at a time t1 and the cosine function at a time t2. So it becomes cos omega c t1 plus pi and cos omega c t2 plus pi. So the cos A cos B, you can apply the formula cos A cos B, it becomes cos A plus B plus cos A minus B by 2. Okay. So therefore, the autocorrelation function of the modulated signal R z of is R z of T1 T2 equal to 1 by 2. Expectation of V of T1 V of T2 into cos A minus B, that is cos omega C T1 minus T2 cos A plus B. So cos omega C T1 plus T2 plus 2 pi. So this is the sum of two components. This is the difference of two components. By omitting some component and by taking tau equal to t1 minus t2, finally we are getting the simplified autocorrelation function for the modulation signal, modulated signal, that is r z of tau equal to 1 by 2 rv of tau cos omega c cos omega c tau, right? So like that we are getting. Then from this autocorrelation function, you can find out what is the power spectrum. So by taking Fourier transform of the autocorrelation, you can get the what is the power spectrum. But already we derived the expression for the cosine function. What is the Fourier transform for the cosine function? So here directly the expression is given for the Fourier transform of the power spectrum of the random process. That is g z of f equal to 1 by 4, the difference frequency component and the sum frequency component. Okay. So coming to the last topic in this session is filtering the random signal or filtered random signal. Okay, you can see this is the filter in the LTS system, linear time invariant system, and it has the impulse h of t. In frequency domain it is h of f, and we can see here the input signal is x of t, whose autocorrelation function is Rx of tau, and whose power spectrum is Gx of Gx of f. And coming to that output is y of t for this filter. Okay, when input x of t is given to the filter, it gives the output y of t, and its corresponding autocorrelation function is Ry of tau, and the power spectrum is Gy of f, right? So this is a basic filtering process of the random signal, right? So the random signal x of t applied to the input of the filter. So the filter generally we are considering LTS system, and it has the transfer function h of f and the impulse response h of t. Then the resulting output signal is given by the convolution. Okay, so the output y of t is the convolution of the input signal x of t and the impulse response h of t. So the y of t equal to minus infinity to plus infinity h of lambda x of t minus lambda d lambda. Here they are using the different notation, but usually many textbook they are following tau symbol, not to because of making a difference. Okay, this lambda is a dummy variable only actually. Okay, So since convolution is a linear operation, the Gaussian input produces the Gaussian output, whose properties are completely described by the mean and autocorrelation function. And we can assume that input signal x of t, output signal y of t, and the impulse response h of t are real, and the input signal is stationary. Okay, under this condition, we can say that y of t will give the stationary power, and the output input cross correlation is the convolution of the impulse response and the input signal x of t. So that the correlation cross correlation function is r y x of input output cross correlation function is represented by r y x of tau, which is equal to the convolution of the impulse response h of tau and the input the autocorrelation function r x of tau, right? So now you can consider this the cross correlation between input output, so which is equal to the expectation of the output signal y and the input signal x at the time t1 and t2, right? Now you can substitute the y of t. Y of t is the convolution of the impulse response and the input signal. So that it is varies from minus integration minus infinity to plus infinity h of lambda expectation of x of t1 minus lambda x of t2 into d lambda, right? So after substituting, because we know that what is the equation for y of t. So y of t is h of lambda x of t minus lambda into d lambda. Here simply we are substituting. Here y of t1 is replaced by the corresponding equation, so that we are getting this autocorrelation cross correlation equation. Then we know that x of t is a stationary random signal, right? We can simplify this expectation of x of t1 minus lambda x of t2 is the autocorrelation, because same signal the different time. So rx of t1 minus lambda comma t2, or we can write rx of t1 minus lambda minus t2. Now we can assume t2 equal to t1 minus lambda. If you replace t2 by t1 minus lambda, so t1 will be cancelled and it becomes a mu minus lambda. So it becomes the t1 minus lambda minus t2 becomes a mu minus lambda, means a tau minus lambda. So therefore the cross correlation of the input output is depend on rx of t minus lambda d lambda, right? It is actually the convolution equation, right? So hence the autocorrelation between input output, that is r y x, is the convolution of the impulse response h and the autocorrelation of the input x, right? That is rx of tau. So similarly, we can find out the correlation function for the output signal y, that is ry of tau. So the ry of tau is the convolution of impulse response into the cross correlation of r xy of tau, right? So we already know what is the r xy of tau. So here we have to substitute. Then h of minus tau, h of tau, it becomes h square of tau. Okay, square of the h, right? The square of the impulse response. Okay, okay. So that from this autocorrelation of the output, we can find out what is the power spectrum density at the output. That is g y of f equal to modulus of h of f squared into g x of f. This is the final expression for the output of the LTI system. What is the power spectrum density of the output of the LTI system? The input is the random signal. So the general formula. So here the G x of f is the input power, G y of f is the output power. This modulus of h of f squared is the squared magnitude of the a system, LTI system. You can call it the squared magnitude of the LTI system. So from this power spectrum density, we can find out what is the autocorrelation for the output signal by taking inverse Fourier transform. By taking inverse Fourier transform, because both are reverse to each other. Okay. Okay. So if you know the power spectrum density, you can find out what is the autocorrelation function. If you know autocorrelation function, then we can find out what is the Fourier transform. Right. What is the power spectrum density? Okay. Then Then by putting at a tau equal to 0, we can get the average power of the output signal. That is y squared bar equal to r y of tau. Means by putting tau equal to 0 in the autocorrelation of the output signal r y of tau, so it becomes r y of 0, which is equal to minus infinity to plus infinity, right? Minus infinity to plus infinity h of f squared g of f squared df. Then the mean of the output signal is my. So finally, we are observing three parameter from the output signal. What is the power spectral density of the output signal? What is the autocorrelation function? And what is the average power from the output signal? Then what is the mean value of the output signal? So the mean value of the output signal is depend on the mean value of the input signal into the magnitude of the impulse response. So the magnitude of the impulse response also calculated by using the integrating that impulse response over the interval minus infinity to plus infinity, right? Okay, so it actually it has only magnitude because impulse, na, so that only at 0 it has the magnitude. So it is h of 0 mx, where h of 0 is the system DC gain. Okay, so this is the basic formula for the Hilbert transform of the random signal in time domain and frequency domain. In time domain, the Hilbert transform equation is hq of t equal to 1 by pi t. In frequency domain, hq of f equal to minus j signum of f. Okay. Okay, thank you. So in today's session, we studied about the remaining top points in the power spectrum estimation of the random signal. So we studied the one expression for the power spectrum estimation of the random signal, that is a digital random wave. Then we studied about the filtered random signal. Okay, thank you.